Dr. Tanushree Ghosh, Assistant Professor from Department of Chemical Engineering at HIT Haldia. Today my topic is basic problem solving on combined processing unit of absorption and distillation processes. This is a flow sheet of the given problem where it is stated as following figure represents the flow sheet for the recovery of acetone from air, and all the compositions are here given on weight basis. We have to make a material balance and determine the quantities of the following streams. So the questions are here arised. First question, water added in the absorber, acetone free air leaving the absorber. Third question, aqueous solution of acetone leaving the absorber. Next question, the amount of distillation product and the bottom product. Last question. So let's discuss about the total flow sheet, what is represented here for the solution of the problem. Here what is observed, the first is absorber, which is absorption unit, and second one is connected with this absorber, that is distillation column. In the absorber there are two inlet streams. One is the air gas mixture which is entered here with flow rate 1400 kg per hour, composition of what is 95% air, 3% acetone, 2% water. And the notation for inlet gas stream is here given G1. The outlet stream, that is for gas stream, that is G2, denoted by G2. Composition is here 99.5% air and 0.5% water. That means here acetone is totally driven out. No more acetone is present in the exit gas stream in G2. And the aqueous solution which is entered as solvent, that is water, pure water, denoted by L1, taking with some acetone which is coming from this entering G1 stream, and this after absorption this acetone into this water stream aqueous solution, when this aqueous solution is leaving from this absorber unit, then the percentage of acetone is raised as 19%, and comparison with the overall composition of water, individual composition of water in this L2 stream is 81%. Now when this L2 stream is entered into the distillation column as feed stream, two products are obtained, that is distillate and bottom product, where in distillate the acetone percentage is given 99%, whereas bottom product is having 4% acetone only. Remaining percentage of water, that means 96% is here water. And similarly in distillate the water percentage will be water 1%. So this is the total flow sheet which is given for the solution of this problem. So let's discuss about how to solve this all the unknown parameters. First, the question which is asked here, water added in the absorber. That means what is the value of L1? It has to be calculated. Next question is acetone free air leaving from the absorber. That means what is the amount of G2? Next, aqueous solution of acetone leaving the absorber. That is L2. Distillate product, that is D, and bottom product, that means what is the value of W. Now all these 5 parameters have to be calculated in the unit of kg per hour, because here G1 is given as 1400 kg per hour. So all the 5 answers are to be evaluated in terms of kg per hour. Next, go for solution. First, we have to take the basis. Basis is here taken, that is gas is entered into the distillation unit with 1400 kg per hour flow rate, that is G1. Now you have to consider that acetone as A, air by B and water by C. So all these symbolic representations are here given for these 3 components which are involved in this processing unit. Now given data, as per given data shown in the flow diagram, that is mass fraction of A in the entering gas stream in G1 will be XA G1 equals to 0.03, and then mass fraction of B in the entering gas stream, that is G1 again XB G1, that is 0.95, mass fraction of C in entering gas stream, that is 0.02, mass fraction of A in exit gas stream G2, that is XaG2, obviously 0 because exit gas stream is not containing any acetone, so 0%, hence the mass fraction becomes mass fraction of A, that means acetone becomes 0. Mass fraction for B in exit gas stream, that means in G2, that is represented by XbG2 equals to 0.995, whereas mass fraction of C in exit gas stream will be 0.0005. And accordingly, similarly, the composition with fraction or mass fraction for L1 stream are given here. XaL1 for acetone, that is 0%, because initially the water which is entered into the absorber, that is having 0% acetone, and XeL1 water, totally pure water, that's why here mass fraction is coming 1. And for the other mass fraction data, XaL2, that is 0.19, XCl2, that is 0.81, XAD, that is the distillate composition for A component acetone, that is 0.99, and for C, that is for water, that is 0.01. These two are for the composition of A and C present in distillate stream. Now the composition of W, that is bottom product, is 0.04 and 0.96 for A component and C component, that means for acetone and water respectively. That two last two are for bottom product composition. Next, first we have to do what? The material balance on absorption column. Absorption column, when we will do the absorption column material balance, first you have to do air balance as tie component, because here when it is entered into the absorber, it is entering as inlet, entering in as inlet in the inlet gas stream, that means in a single stream it is entering, and when it leaves from the absorber, again as single stream it is leaving. So that's why air is here considered as tie component. So if we do the material balance for air on absorption column, then we'll get definitely one unknown parameter value. Now G1 into XbG1, this is the air balance as tie component on absorption column. G1 into XbG1 equals to G2 into XbG2. This is the general equation which can be represented in this way. After putting the value of G1, XbG1 and the value of XbG2, all these three parameters are known, where G2 is only unknown. So simply it can be calculated G2, and the value is coming 1000 336.68 kg per hour, which is the answer of question B actually. Next, if you do the acetone balance on absorption column, then we can write the general equation in this way: G1 into XaG1 plus L1 into XaL1 equals to G2 into XbG2 plus L2 into XaL2. Now here all the parameters value are given except L1 and L2. So L1 is L1 does not matter because L1 is multiplied here with 0 value because XaL1 value is 0. So only L2 value is left to determine. So simply it is here also calculated L2 after putting the value of G1, G2, XaG1, XbG1, XbG2 and XaL2, we can get the value of L2, which is the answer of C. Now after putting these two value G2 and L2 and G1 already given in the problem, so putting this all three parameter L2, G2 and G1, we can get the value of L1 if we put the values, three values in the overall material balance on absorption column. That is G1 plus L1 equals to G2 plus L2. This is the overall material balance on absorption column. So hence we can put here all the known parameter value. G1 already given in the problem, G2 and L2 already calculated in the previous steps. So L1, hence L1 can be calculated in this way and it is coming out as 157.73 kg per hour. Next we can go for material balance on distillation column. First, we may write overall material balance, that is L2, which is feed stream for distillation column, that equals to D plus W, distillate amount plus bottom product amount. Here L2 is already evaluated in the previous calculation. Hence we can put here the value of L2. Only D and W are here now left for calculation. This is, we can write equation 1. Next, component material balance for A component, we can write in this way for distillation column, that is L2 into XaL2 equals to D into XaD plus W into XaW. Now here we can see that L2 value is known, XaL2 already given in the problem statement and XaD value already given and XaW also given. So only D and W again here are left for determining. So you can write here equation 2. So after by solving this equation 1 and 2, we can get the value D as 34.9 kg per hour and W equals to, it is coming 186.15 kg per hour, which are the solution of question D and E respectively. That's all. Thank you.